can see some kind of quantumness emerge from a classical neural network, the one that machine learning engineers study. Now, I will get a little bit into more speculative topics of how Lorentz invariance or how field theories may emerge, but that's not going to be a primary aspect of the talk. So here I have a long list of archive articles. And of course, if I would be giving a talk where I describe everything in details, it would take us hours, and we're not going to do that. So I'll just take the main ingredients from all those steps and see whether whether an interesting picture emerges. But for those who are really interested into going to the original articles, here's a list. There is a bunch of them on the growing list on machine learning part of the problem, where we're just concentrating on the algorithmic aspects of neural networks without necessarily having any relevance to physics. And yet, in all those attempts, we see that something physics-like emerges. So you see some kind of emergence of particles, you see emergence of grand canonical ensembles, etc. And then there are some articles, a bunch of articles again, of how you can model dynamics of neural networks, again, classical neural networks, the standard ones, artificial, whatever you want to call it. And then how from that you can see very interesting non-trivial emergent behaviors. So we do not put anything by hand. We do not assume that quantum mechanics must hold, or general relativity must hold, or Hamiltonian mechanics must hold. All of those things must be somehow derived. If they are derived, then we kind of say, all right, then we can make progress further and see what kind of interesting behavior we can observe. For those who have very diverse interests, there are also articles about how you can apply this mathematical framework to model more complex phenomena such as biological evolution. But again, I won't talk about this. Everything which is highlighted on this page, I will mention one way or another. Everything is not highlighted. I will not have time to talk about. Okay, so the starting point is only one slide where I will just define exactly what I mean by a neural network. Now, of course, machine learning scientists write books describing this slide. I will only make a very simple assumption, a necessary and sufficient assumption for whatever I'm going to do next. So for me, a neural network consists of those 7 components. First is the state vector of neurons, which can be a real number. There are ways to generalize it to make this number complex, but that doesn't really give you anything that you don't have before. So this doesn't give you additional abilities for the system to learn, but complicates things. So we'll leave it as real numbers, which makes things simpler. Now, those neurons can be both in what I call bulk and the boundary. The boundary neurons is what usually machine learning people think as the data set, right? So you have a data set, you're learning handwritten images, or learning to identify cats and dogs. Whatever your learning objective is, those are the boundary neurons. And so to define them, we just need a projection operator that will take you to that subspace. Okay, so far so good. So this is just to define 2 types of neurons. The next one is what I just mentioned, the training data set. So it's some probability distribution over those boundary neurons. Now here, it's a simple example where it's just a distribution over states. You can have a distribution over trajectories, more interesting, and usually such things become important for learning as well if there's some kind of ordering in the training data. Now there is this, at first sight, simple object matrix, but then again, once you introduce this matrix, you can start thinking about matrix or weight matrix connecting different neurons. You can start thinking about neural network as a graph. And so with all of the difficulties and complications that come with it. Now it's a weighted graph, it's a weighted directed graph in general. However, in machine learning literature, very often they restrict themselves to only nilpotent matrices, which corresponds to feed-forward architecture. Again, we don't want to make any assumptions unless they're absolutely necessary. For us, it will be just some weight matrix, arbitrary weight matrix. Again, real numbers, everything. There's this bias vector, which isn't really that much important, and so you actually can work without it, but I'll keep it just to keep things consistent with the literature. And then 6 and 7 are the most important aspects of artificial neural networks, which is what I'm describing here. The first one tells you how the state vector changes, how the neurons change. And there is a well-defined deterministic rule for that. And then the second one describes how the biases and weights change, and there is a different rule for that. So this one is usually, you define a loss function, and then you're trying to move in the direction that minimizes it. You may use, for example, stochastic gradient descent method for that. So two types of dynamics, two types of, if we have to summarize the slide, there are two types of variables. There's this X variable, state of neurons. I call it non-trainable variable. And then there is W, which is a trainable variable. And those two variables evolve according to different rules, which is important. I will like to stress on this last variable because really that's where all of the complexity, this seventh item, because that's where all of the complexity coming in. You know, having a state vector that changes with time according to some rule, we very well know how to handle. We have an example of phase space, the vector in the phase space that changes according to the Hamiltonian mechanics. We can have examples of vectors in the Hilbert space that changes according to unitary evolution. We know all that, but they all those variables all change according to some rule, similar to activation dynamics here. Now, in addition to that, imagine that not only the state changes, but the Hamiltonian itself that describes the dynamics start changing. There are some other variables that are being adjusted. And that complicates things a lot. Nevertheless, that also gives you a lot more ability of what kind of things you can model with such a system. Okay, so one slide describing everything there is to know for our purpose in machine learning. Now let's move what we can do with it. Okay, so now what we want to do, we want to look at that system and see, all right, if I am not to pay attention to what individual neurons do, kind of have a coarse-grained picture, zoom out, what can I say? What can I say about the dynamics? Are there any phenomenological parameters, thermodynamic macroscopic parameters that can describe the evolution? And if there are, what are their laws? What are the equations that describe their dynamics? So let's start with something simple. We'll try to go to equilibrium, meaning that you have a neural network that learned for a very long time. It learned this particular data set, so distribution of the boundary neurons. Now, every time you propagate the signal through the neural network, there is some X bar, which is the state of neurons in the bulk that takes place. You change the boundary distribution, the boundary state. Again, there's some other state in the bulk. Very similar what we do in classical physics, right? Once you specify the boundary of the field, you can solve for it in the bulk. Okay, good. But now we want to go to ensembles. Instead of taking this ensemble where you have a product of delta function in the boundary distribution, which is hard to analyze analytically, you go to what you usually do, you replace it, this microcanonical kind of ensemble with a canonical ensemble, something of this side. Now, what is important here that there is this H, the one most important function on the space of states of neurons and biases and weights. So in the space of both trainable and non-trainable parameters. So X is non-trainable, B and W are trainable. And we assume that the system went to the local equilibrium. And then at that local equilibrium, the only thing we know is the average loss function. So it must have dropped to some small value. It still fluctuates as the learning proceeds, but there is some. And then you say, okay, what would be the distribution? Then you can take the maximum entropy principle and use it to derive what the distribution would be, given the constraint on the average loss. And then you obtain the usual canonical distribution of this type. Now, there is this parameter beta. Now, in the case of the optimization problem that I described, maximum entropy problem, finding the distribution that has maximum entropy given the constraint. This beta is nothing but the Lagrange multiplier, right? Okay, but once you have that, you do the usual statistical mechanics. You define the partition function. You can, given the partition function, you can find average loss, free energy, entropy, and all those things can be compared with the actual experiment, numerical experiment you do. Now, you have to be careful about everything you do because, again, there's not just activation dynamics, which was number 6 in my list. There's also the learning dynamics. So things that you expect the system to do in physics, for example, entropy should grow, may not necessarily happen in that system. The whole point of the learning dynamics is to actually try to learn the boundary data set. So it kind of wants to create a redundant information about the boundary in the bulk, wants to memorize it. And so not everything that you are familiar with physics will hold here. After all, our mathematics that defined microscopic dynamics was somewhat different. Okay, so now let's see this was equilibrium. That's what happens in equilibrium. And you have all those quantities. Now let's try to move to non-equilibrium dynamics, where the free energy can change. Then we already identified those two types of parameters. One I call trainable, one non-trainable. But let's think about this non-trainable parameters, axis, states of neurons, as some hidden variables. You integrate it over them. You don't have to think about right now as a hidden variables in quantum mechanics. No, just some variables you coarse-grained over, integrated over. Okay, once you did this, the only relevant quantity for you is this free energy, and it depends on all of your trainable parameters. Now, in this slide, I denote trainable parameters as B and W. Moving forward, I combine them into Q. So Q's are the trainable variables. And X disappears because I've integrated them. And then you ask, okay, how will the distribution, how will the Q's, how the distribution of Q's will change with time? And so what you have this two conditions. On the shorter time scales, you have the condition that this free energy must satisfy. The total change in the free energy must be expressed this way as the change in the explicit change in the free energy and implicit in Q variables. Now, equation 7 would be all there is, but in machine learning, according to the learning dynamics, we have an extra piece of information. We know how the trainable variables change. They change according to the gradient descent. So equation 11. So when you plug it in, you actually get an equation. Now it's not very trivial. Equation 7 was trivial. 8 is less trivial because now it uses the knowledge of how the trainable variables move. Okay, and now in addition to that, we also set up a diffusion type equation when because we try to analyze how does the distribution of the trainable variables change. So now to do this actual experiment, it's not enough for you to have like one run of the machine learning simulation, right? You have to do many runs, and now with the Q, and every time you do your run, the trainable variables come to a different state and they evolve differently. So then you can, by doing many runs, you can study how the distribution of the trainable variables would evolve. So basically you have this two equations, condition 8 and Fokker-Planck type equation 10. Now, it isn't exactly Fokker-Planck because now this F is not a fixed potential, because then if it was a fixed, if it didn't depend on time, that would be exactly Fokker-Planck with the diffusion and drift, but it isn't. And so now you have both of those variables, F and P functions, dynamical. And so really, you cannot solve one without solving another. You have to solve them simultaneously. And that's what being said here, that usually in optimization problem, one first solve for F, you know F, and then you know how to solve Fokker-Planck on top of this. Here, the equation is trickier, and you have to simultaneously make sure that equation for F and satisfy. So now for F and Fokker-Planck is satisfied. So now the idea is to use this principle of the stationary entropy production, which says that the dynamics should be such that the entropy production is satisfied, given that stationary entropy production is stationary, given the equations on the previous slide are satisfied. And then you have, this is the entropy production that you can just write down using the equations above. And again, this is an equation just for the change in SQ. But then you have this additional constraint that you impose on the free energy production. You say that the free energy production must be an average given by some value. Okay, so and again, just like what you would have if you set up the maximum entropy principle for the time-independent distribution and you obtain something like a canonical ensemble here, it's a bit trickier because you're not obtaining the distribution P which doesn't depend on time, you're obtaining distribution of trajectories, how the P of Q and T changes, how F of Q and T changes. There's no quantum mechanics here. This is completely classical analysis. You can move things around and take this equation. You can complete the squares. Once you complete the square, there's certain quantities that are useful to define. We don't have to go into details, but the point is once you have all of that, you still don't have quantum mechanics. What you obtain action-like functional, which if you vary with respect to P and F tilde, now F tilde is like shifted free energy from the previous slides, then you obtain Madelung type equation. So again, not quantum mechanics yet, so this is not Schrödinger equation, but we're getting close. All right, and then this equations, U is the velocity of the quantum fluid in a Madelung equation in the quantum hydrodynamic sense. The M is something that plays the role of the mass. Now here it is defined as 1 over gamma, where gamma is the learning rate in the previous slide. So this is this gamma. And then something that, again, plays the role of H bar, because we just say, let's define and call it H bar for the reason that will become clear later. And you see this H bar has the diffusion coefficient, which is related to the mini batch size in learning, is gamma, which is related to the learning rate. It has alpha, which is Lagrange multiplier for this optimization problem that you have. Okay, fine. So we got Madelung equations, as very often people mistake Madelung equation and claim this is Schrödinger equation. It isn't. There is one more condition that needs to be satisfied. And the condition is written here. You really need F to have this finite shift, which is unobservable, because F will play the role of the quantum phase. And we know that if you change this F, it should be tilde here, F tilde. If you change F tilde by 2 pi, then this shouldn't 2 pi times H, then this should not be observable. So you have to have this constant shift of F where this N can be arbitrary. Continuous changes should be observable, but this discrete change with a certain step should not. And if you have that, if F would happen to be such that its constant shift is unobservable, then you can claim yes, and for a certain mu, not for arbitrary mu, then you would claim yes, the dynamics is of the Schrödinger type. Right now it's a big if, because why would any shift in F be unobservable? Now, when you take definitions of both H bar and mu, you obtain this equation for alpha. Remember, alpha is a Lagrange multiplier. And if you carry on the calculations, you see that this condition is not always satisfied, and there are only two solutions. It's quadratic equation, so there are only two solutions. And so the solutions exist only if this inequality is satisfied. Now, if it isn't satisfied, and all this gamma, mu, d are again parameters of your learning system. So if, for example, the set of these parameters is such that it's greater than 4 pi, then that's it. There is no quantumness. There is no Schrödinger equation. There is just a Madelung equation. But if the system has advanced enough algorithms such that it can adjust those variables, for example, diffusion coefficient is what's called the mini batch size. If you can change that, gamma is the learning rate. If you can change that, if you are smart enough in changing that the system can tune its parameters such that this inequality is satisfied. Okay, and that's what's needed. That's the conclusion. So to have an emergent quantumness, you need, in addition to this discreteness, you also need, which is unobservable, you also need the parameter to be of a certain size. Okay, so moving forward, again, I already mentioned that if you have a system that is smart enough to do that, that this will happen, but not in any machine learning system, you will definitely have that. But now let's go to this condition, which I call the multivaluedness condition. When can it be satisfied? Well, this is an example when you should move away from the canonical ensemble of neurons, where the number of neurons is fixed, to the grand canonical ensemble, when the number of neurons is not fixed. So imagine you have some kind of learning algorithms, and then you have available resources, computational resources. When you need additional resources, you borrow a neuron. If you don't need it, you give it back. So you have a pool of neurons that you only use when you need it. Now, taking all of the neurons at once is not a good idea, because that would confuse only the system, and will start overfitting, and other problems will have. Using very few neurons also not a good idea, because it will not be able to learn anything. And so there is, it's very reasonable that the most efficient algorithm would be the one that has this ability to bring in and out neurons for the system. And then we move from the canonical ensemble to the grand canonical ensemble. And if moreover we say, well, the number of actually active neurons are not observable, then really you have this discontinuity, where now theta is the grand canonical partition function. Okay, and mu also plays a role now, right? So mu before was just a number, now it's kind of a chemical potential of the neurons. If I added new neurons, how much did my loss function change? Equivalent to that. Okay, or if I remove it. Okay, very good. So that's kind of the main conclusion from the first part of the talk. Basically, just to summarize, because that's the main part of the talk, is that you can have emergent quantumness in the artificial neural networks, or in any networks that follow this classical path, but you do need two ingredients. So first of all, it has to have a clever enough algorithm such that the parameters are carefully adjusted. And the second one is that you have to have a pool of neurons, and so the number of active neurons is not fixed. Now, we're not talking about any Bell inequalities here. And if we are to think about that, well, how that, if we are, well, first of all, there are two things we can take from this. First one is, okay, so can we now use artificial neural network to perform efficient quantum computation? That's a big if. That's, I guess, using just the mathematics we just described to make use of the quantum advantages that we know about. But the other thing, you say, all right, but maybe we can take this framework and now also model quantum systems of the physical world, where we would not have any any Hilbert spaces or unitary dynamics. It would just be only an approximate description of the true dynamics. Now, in the first case, you're ready to go. You can do that. For the second case, you have to be careful because this chemical potential will not just be a constant. And so for a small enough system, there will be fluctuations. And so you will see that these discrete changes are not exactly the same as you change the number of neurons. And so deviations of the standard quantum mechanics should occur. So this would say, if the world is a neural network, which is the title that was advertised, then there is a way to check it. The quantum mechanics must break down for a sufficiently small system when you see that mu is actually changing. It depends on the n. Okay, so and that brings me to the next point. Okay, so if we do insist that two directions, right? If we do insist that this is an efficient algorithm, let's try to implement it. Let's try to create this bath of neurons and algorithms where you would use neurons or give it away when they're not useful. And this is what we've done in this paper from Archive from the last year, when we tried to see whether being able to add neurons to the system and remove it is beneficial, and we saw some advantages of that. But again, there is the second direction of seeing whether it is a useful way to modeling quantum mechanics system. But we put all of the Bell's theorem aside, because really this would imply very much non-locality of the hidden variables in that sense. And from the point of view of neural networks, there's no problem with that, because any neuron can be connected to any other neuron. So in this paradigm of the world as a neural network, that's not a problem. Okay, now having Schrödinger equations derived may be a nice thing to do, even if it's approximate. but this is a whole story. There's a lot more complexity in the universe. And so one thing I want to study next, describe next, is how can you actually get something like Lorentz invariance emerge? A lot more complex problem. Now, and then, of course, after that, once you have Lorentz invariance emerge, you may ask, can you have Einstein equations emerge? Can you make gravity emerge? So this second part, I wouldn't have time to talk about. It is described in this paper from 2021. But I will talk about roughly what it means for the Lorentz symmetry to emerge. Well, before that happens, the space should emerge. And the simplest model of how the space may emerge for a single neuron, we just take a single neuron, is that upon the dynamics, it changes, it comes into the equilibrium state where its state goes through some number of discrete states, quasi-periodic. And so this is what I illustrate here on the equation 31. So there is some state at time t, there is some state in t+1, at some state at d, and back to the previous one. Now, I say it's quasi-periodic because this will kind of describe the location of the particle in the emergent space, but then it will continue this quasi-periodicity. And so all of those locations in the emergent space will change. We keep for concreteness d equals to 3. And there's an assumption that makes that, again, that entropy production is what's relevant. You want to extremize it. But we are saying that, single neuron, the overall entropy will be the sum of the entropies of the individual neurons. And we zoom in only on a single neuron. We're not interested in the gravity so far. At this point, we're just interested to see is there approximate Lorentz symmetry can emerge. Okay, so then if those are the states of the position of the neurons in the emergent space, then we can define this displacement in this emergent space, how much the positions in the emergent space change. And that's what I denote as x dot a I, where x dot means it's a derivative. Upper index indicates the dimensionality, you go through 1 to 3 for three-dimensional space, and I indicates the neuron number. So we just zoom in on one neuron and see what happens. Now, what we know from the learning system, and that's something I've identified before, that there are two things happen with it. First of all, due to the activation dynamics, entropy seems to grow. That's the usual type of dynamics. You have a predetermined law, you kind of iterate it, and then the outcome of this is the entropy grows. You have positive Lyapunov exponents, and so the thing is inconsistent with what our usual view of the dynamics. But now you have a second type of dynamics, and then for that one, entropy decays. So there's always, for any neurons or any subsystem, there's these two effects. If you turn off learning, entropy will tend to grow. If you turn on learning, then entropy can do both, can decay and grow. Okay, and the idea is then to take this ds, the change in the entropy or entropy production, and to just decompose in two parts. One part which is responsible for the entropy growth, and the one part with responsible for the entropy decay. And you say that entropy growth has with this displacements, with the changes. So if the state of the system is completely periodic, and there is no changes when you go through this, then there is no entropy being produced, and entropy production seems to be is zero. So that's the model. But if those displacements do change, then they have some non-zero entropy production. And then you put all of it and say, okay, well, all I'm going to do is now to model the overall entropy change as positive one due to the activation dynamics, negative one due to learning. And for the positive one, I assume it only depends on computational time. So really, I can define this monotonic function this way, which will play a role of some kind of time-like coordinates in once we get this approximate emergence of relativity of Lorentz invariance. And the other one is negative entropy production, which is we model as a functions of displacements. But again, we said that if the displacement is zero, there should be no entropy production. And so if you expand around it, really you have some kind of quadratic expansion where Gi is AAB is a positive definite matrix, 3x3 matrix. Okay, so then you can combine this together, and as you might expect, really we can write it in a covariant form in this way. Of course, here it's a preferred coordinate system. We have G00 equals to 1. We have all those components equal to 0. But the statement here is the following: if microscopically you can only observe the change in the entropy, then you are free to make a transformation on this. If you cannot observe actually displacement, but you are only the entropy, then this is the only quantity which is relevant. And all of the displacement vectors, we can think about them as 4 vectors in the tangent space of allocation of a neuron in that emergent space. Okay, and then there are, of course, 3 possibilities. There's a given neuron, or maybe not even a neuron, maybe there are a few neurons equilibrium, then the entropy production would be 0, and so that would correspond to null-like vectors. Now, if entropy production is dominated by the stochastic dynamics, by the activation dynamics, then it would be possible, and that's the usual case we see. And all of a sudden, if you do have a rare case when the system is actually learning, reduces its entropy, then it corresponds to the space-like vectors. Not clear what's the point of those vectors. So again, I mean, whether they are stable or unstable, most likely they're unstable because the system is not in isolation. So once it starts learning and entropy drops, it acquires new information through the data set, and that will probably prevent it to continue the path of this space-like direction for too long. So that's Lorentz invariance, and I have a few more minutes. Let me just show it again. It's somewhat disconnected from the first part of the talk when I talk about quantum mechanics. The second part of the talk, well, a couple of slides, Soren Lorentz invariances, and the point was that for the quantum to emerge, you have to follow carefully trainable variables, and you can coarse grain over non-trainable. Now, for Lorentz invariance to emerge, you have to go into a deeper picture and actually see how the non-trainable variables evolve. So now I want to go to something that is really fun and interesting. And this slide has no new information to you. Every high schooler, well, every student had seen that. This is just an illustration of a type of how particles and fields may emerge. Now, the first slide is not their emergence, but what we think they are. We have charged particles which move in the electromagnetic field. And this type of behavior will be something that we will use to show how the similar behavior can emerge from a learning system that knows nothing about electric or magnetic field. Okay, so now you consider charged particles, and there are some sources. Now, to determine acceleration, what we have to do is to determine the electric and magnetic field, and once we know, and in all positions, and once we know that, we can perform the differentiation and find the once we know them, we can find the Coulomb force, the force that would be acting on those particles, right? So the key object here is this phi. So this is you have a green function multiplied by sources, and so this is the one that tells us the relevant information about position of follow. So now think about a particle as some autonomous vehicle. So you are inside of it, and you want to move as if you are a charged particle. So the actual positions of all the particles around you is irrelevant. All you want to do is to come up with the integral of all that information. You want to know the positions of other particles, but then you multiply by this propagator, and then you get at the end some bosonic field that will tell you, okay, so now you're ready to make a motion move in the direction of its gradient. But the fine-grained detail is not important. Okay, so that's the standard picture. And so let's wrap it up and see exactly what things are. So for the local view, you have, and the local view, which I just mentioned, you have electromagnetic field that is around and that contains only irrelevant information that you need to move. Now, for the global view, you don't do that. You actually connect the positions of all other particles and do this integral for yourself. Each particle does that. That seems to be an abuse of resources, but you can do that. But then there are two pictures. One physical is the usual, the Lagrangian, where we have fermionic fields, we have bosonic fields, and those fermions we think about as the autonomous decision-making agents or particles, and then bosons as relevant information for them to know how to move. And that's a physical view with the Lagrangian. The learning view is you do the opposite. You try to define the loss function for some objective, and then you will make motions, decide where to move, where to accelerate, defining for these objections. So then each autonomous particle is kind of a fermion, and the relevant information that you obtain is a boson. And so this the different views, they're equivalent. And so for every physical view, you should be able to come up with a learning view and vice versa. Now, of course, we know that the physical view is very useful. It's very compact. You just write down Lagrangian. We don't know if the learning view will give us any new insight, but let me just show a simulation of where the particles are actually autonomous vehicles. And so each of them actually have their local objective of getting to the destination. But if we remove this objective, what you will see will just soup of cars moving around. And this soup of cars does not know anything about field. It doesn't know anything about bosons, but has some learning objective. And all of the information about how they turn left and right is hidden in the relevant information they keep about the environment. And so by changing loss function, we can make this cars or particles move in any way we want. There's no quantumness, it's completely classical. There's no Lorentz invariance. There is only the Galilean invariance, but nevertheless, this is with the direction that you can go, how to describe the motion of particle-like system, how the particles would emerge as like autonomous decision-making units, and how the bosonic fields would emerge as the invariants that are relevant for the decision-making of those cars. Okay, so I think I am running out of time, so let me wrap it up. If I'm able to move. Yeah, so this are the main results. Again, bunch of, there's no way I was able to actually go into details describing them. This is a completely new approach. Of course, as I said, you're not making assumption about anything of classical physics, quantum physics, so everything has to be rederived. Nothing is for free here. And so the stationary entropy production principle was of key importance. It was first introduced here. Now, quantum phase isn't just some mysterious object. It has a particular meaning in this setup. It's a free energy of non-trainable variables. So it's a completely statistical approach in this sense. Now, Madelung equation you get more or less for free. The Schrödinger equation doesn't come for free, and you really need the grand canonical ensemble of neurons. So you have to tune your algorithms if you want to see something of this type emerge. And again, at this point, you have to decide, okay, do I want to model the real quantum system as a machine learning, as a learning system? And then there is, of course, they're not going to be exact match, and there will be discrepancies. Or do I just want to use the quantumness to produce more efficient algorithms? And there you don't have any, your hands are not tied. Okay, so now, and that's what I say here. So really, you need the self-tuned parameters. The algorithm has to be clever to do that. Now, the Lorentz symmetry is something that can emerge. Again, there is still, having Lorentz symmetry isn't enough to get gravity, and we know there is a lot more to be done, and this was mentioned and discussed in this paper. To have a grand canonical ensemble of neurons that is efficient, this is necessary for the Schrödinger equation to emerge. You also need special algorithms, which is described here and tested on machine learning systems. And the field theories is something we are trying to investigate now. This is a new topic. The duality of this that I mentioned in passing, that Lagrangian description, physical description, and learning description, loss function description, whether there's a connection between them, when you can have one but not another. What is the loss function for electromagnetic field, and what is the loss function for the effective autonomous vehicles? All these questions are still in the air, but not something that should be addressed. Thank you.
Okay, thank you, Vitaly. Questions, but please be short. Roman.
Vitaly, thank you very much for your interesting talk. Just like to ask you to explain a little what is the physical meaning of the learning rate. As I saw in one of your slides, it is inversely proportional to some mass. And what kind of mass? Can you explain a little bit?
Yeah. So mass is just a parameter that you don't have mass. You have this, right? That what appears in your equations. But you're saying, I've seen these equations, and I know that for these equations, this is the place where mass appears. Okay, so let's call it mass. But the learning rate isn't only appearing in the mass; it's also appearing here, like in the Planck constant. So. But it just doesn't appear there alone. It appears with the diffusion coefficient and the Lagrange multiplier. So, but the idea is this. Yes. So if you take your learning rate, let's take it to infinity, right? So if you take it to infinity, then this becomes a very massless particle. It learns very fast, goes to the equilibrium very fast. Now you cannot afford to do this for all learning systems, because most all learning systems are very complex. and everybody who has taken this to infinity know what's going to happen. It's going to be very unstable. So you will have you'll be in equilibrium very fast. But then it will, the loss function will start jumping up and down. But yeah, this is a good question, because really our hands are tied. We have gamma, D, and alpha, and out of those we want to form understanding of the things that are related. Now, I will quickly just tell one more remark, because we have this chemical potential that's related to H bar. Now, what is a chemical potential? It is again a constraint that imposes on the number of neurons. So if you think about optimization problem, so that's what H bar is. It is related to the number of neurons, the constraint imposed on the number of neurons. It's just a related question. Thank you.
Thank you.
No questions?
And if you will present during the discussion, I will ask